lecture. There are quite a few people outside. They'll probably sprinkle in. So we have second part of Sandy. Irani, please.
All right. Good morning, everyone. So I'm just going to do a little recap of where we were and then start right in again. So we had defined the class NP last time. So a problem is an NP if we have a polynomial size uniform circuit family, generally a polytime algorithm, however you decide to define it. So if X is in the language, there's some certificate Y or witness that you can efficiently verify that it's in the language. And if it's not in the language, no matter what witness I give you, you're not going to believe me when I tell you it's in the language. So there's nothing that I can do to convince you that it's in the language. So we have a quantum, and we're going to, I stepped through a sketch of the fact that Boolean satisfiability is NP complete. And I'm going to sketch it one more time. And now we have the quantum version of NP. So now instead of a polynomial time classical algorithm, we have a quantum circuit family. If X is in the language, quantum, the witnesses are now also quantum. So if X is in the language, there's a poly-size quantum witness so that your circuit will accept with probably at least 2/3. If it's not in the language, no matter what witness the circuit is given, it will accept with probably at most 1/3. And the name of the game today is to show that local Hamiltonian is QMA complete. Okay? And we showed last time that we can boost these probabilities to be exponentially low and high, close to 1 and 0. Okay? Now, Dorit actually gave me yesterday a really nice way to step through Cook-Levin that parallels the quantum more closely. So I'm going to do that today. So we'll step through it one more time. So here's the general framework of what a reduction will look like. So we have a generic language in NP. We're asking is X in the language? And this is our circuit. And it's in the language if and only if there's a string that causes this circuit to accept. Okay? And we translate that into a Boolean formula. The Boolean formula depends on X. And the Boolean formula is satisfiable. In other words, there's a way to assign assignments to the Boolean variables that causes it to accept if and only if X is in the language. So if and only if this circuit has a string that causes it to accept. Okay, so it's sort of a transformation of circuits to constraints. So if I have a circuit that can do this verification deterministically, we know that there exists a reversible circuit. Okay, because we know that in general circuits can be made reversible. And since that will parallel the quantum case, we're going to use that. Okay, so here's my circuit that does the verification. And now I want to translate this into a set of constraints or a Boolean formula. Okay, so what I'm going to do is create a Boolean variable for every wire in my circuit for every time step. Okay, so if I have m wires and t plus 1 t gates, then I have t plus 1 time steps, and I've added m times t plus 1 Boolean variables. Okay, so each column represents the state of my circuit after a certain number of gates have been applied. Okay, and the point is, and I'm just going to sort of sketch it very lightly, is that the fact that we can enforce that the Boolean variables actually do represent a correct computation of the circuit using only local constraints. Okay, so for example, if there's no gate, I just want to say that the value of these two variables has to be the same. If there is a gate, then I'm just going to have some constraint that says the input-output relationship of those 4 variables has to respect what the gate does. Okay, so these are all local constraints. I could express those using a Boolean formula, and that Boolean formula is satisfied if and only if this corresponds to a correct computation of the circuit. Okay, all right, good. So now we want to do the same thing in the quantum version. We're asking, is X in the language? And now we have a quantum circuit that does this verification. So X is in the language, if and only if.
Why do you have to add many Boolean variables? Why do you use the fact that you added variables? You had on these slides.
Right.
Where did you use it? Just to put constraints on these slides?
So what I'm doing is I'm creating a whole Boolean expression that's satisfiable if and only if this circuit accepts, okay? So I'm using the variables to sort of mark what the circuit is doing at each point in time. Yeah.
It's basically, in order to make these constraints local, you have to.
Yeah, this is what I,
Yeah.
the locality.
Yes, for the locality.
This was my
Yeah. Okay, so a similar thing, we have a quantum circuit, and X is in the language if and only if there's a quantum state that causes the circuit to accept with high probability. And we're going to transform this circuit into a Hamiltonian, a local Hamiltonian problem. So the Hamiltonian that we're going to construct certainly depends on X. So we have a Hamiltonian and thresholds, and we want to create this Hamiltonian so that there's the ground energy of this Hamiltonian is less than E or greater than or equal to E plus delta, depending on whether there exists a witness that causes this circuit to accept. Okay, so it's just a sort of a quantum version of what we just saw before. We're going to start with log K local and then move to 5 local, okay, depending on how far we get. And I'll always use capital T to denote the number of gates in my circuit. Okay, so here's the picture that we just saw for the classical world. And now we kind of want to do something similar for the quantum world, okay? So here's the state of my circuit at the beginning. Here's the state after 1 gate, 2 gates, and all the way to the end. So I have T plus 1 different states that I'd like to encode in some way, okay? We're going to do something similar to this, but there was a question, you know, the natural thing that you would think of is to put a qubit at each one of these intersection points, just like we did in the Boolean case, okay? And then try and use local checks to make sure that the circuit is doing what it's supposed to do, okay? And there's a problem with that, and that I made a slide to show why the problem with that is. Let's suppose we're just trying to do something as simple as just execute the identity gate. So our local checks need to check that this state is the same as this state, okay? And here's an example where they're not different, okay? Not the same.
But they are all
No, where they are different, sorry. But I can't, there's no local check that I can do to detect the fact that they're different. So there's something, this is a bad case that I want my local checks to detect, but there's nothing that I can do to detect them. So this isn't going to work. So what we do instead, so no local check to detect this problem. So what we're going to do instead is add an additional register, which is a clock. Okay? And what we're going to do is create a state that's in quantum superposition. So now the quantum superposition encodes each time step of my circuit. Okay? So for right now, I'm going to use a binary clock. So, and I'm just, for simplicity, t is the power of 2. I can add identity gates to make it so. It's just nice and clean to go all the way from 0s to 1s. So here's my so here's the progress of the circuit at each point in time. And each one of these states is entangled with a different clock state. Okay? So the name of the game now is, what I want is I want the ground state of my Hamiltonian to be this state, which is the uniform superposition of all these different snapshots of the circuit entangled with this clock state. All right?
Is it clear that the problem that you posed has been solved? So can you distinguish 0, 0, 0 plus 1, 1, 1, 1 from 0, 0, 0 minus 1, 1, 1?
You can't, wait.
In this way.
Oh, yeah, because I'm, yeah, I've got,
Each of these vectors sits now in the orthogonal space. How do you compare two vectors?
Yeah.
Is the question clear?
yeah,
Should I
Go ahead.
should I take
Yeah.
it? So the whole point is that locally, if you have a state alpha and a state beta, which their reduced density matrices are the same, then if you have alpha tensor beta, there's no way to locally check that because their reduced density matrices on any small number of qubits
yeah.
is
But he's asking in
yeah,
this
I know,
case
I know.
that there's, a, yeah.
I know. I know. But then the miracle of Kitaev's idea, and that appears in many places, is that even is that if you add a single qubit that is entangled to alpha and beta, so you have 0 alpha plus 1 beta, and alpha and beta can be as large as you want. The reduced density matrix of alpha of that extra qubit tells you something about, tells you almost everything about the inner product between alpha and beta. So you transfer the local checks on alpha and beta to a local check on the qubit that is entangled to them. And that qubit will carry the information about the inner product between alpha and beta.
Yes. But when I reduce, I don't reduce over the extra qubit.
You reduce to the
yeah.
reduced density matrix of just that qubit. That qubit will be
Yeah.
if alpha and beta are orthogonal, it will be completely mixed. If alpha and beta are the same, it will be in the state 0 plus 1.
Yes.
Yeah. All right. And by the way, I think Atayev credits Feynman with this idea, so I think it goes back further.
And I'll show actually this in my talk later today.
Okay. All right. So let's just start with a simpler problem. Forget the computational space. Let's just try and create this as a ground state first, as a warm-up. Okay. So this is just the superposition of the clock states. It's not actually doing anything with the circuit yet. Okay. All right. So here's the Hamiltonian that we're going to use, and I'm going to let's unpack this a little bit. So I'm summing from 0 to t minus 1, and what does this this term actually do? If I look at one of these terms, and I write it out in matrix form, this is the little matrix that I get. Okay, so this is in the t plus 1 basis. Okay, so I have positive diagonal terms. I needed this needs a minus sign here. A minus sign there. So, but the point is that it has an eigenstate, 1, 1, has eigenvalue 0. This is the ground state of this little matrix. So basically what this says is if you want to be in the ground state, then the amplitude on t needs to be equal to the amplitude on t plus 1. Okay? And now we're adding these up over all the t's. So the amplitude on 0 has to be the same as 1, 1 has to be the same as 2, on down. Okay? This is the actual sum of the matrices. So if I look at this Hamiltonian out in the 0 through t basis, this is the matrix that I get. And it's not too hard to see that all of the rows sum to 0. So if I have an even superposition, equal superposition vector, then I'm going to get 0 out. Okay? So this state here is in fact a 0 eigenstate of this matrix. And notice, though, but this is where the log operations come from. In these clock states, I'm potentially changing as many as s bits, all the bits of the clock, if I'm counting in binary. So this is a log t operation. Okay, so here's the propagation matrix that we end up with. We have an eigenvalue of 0. Okay, but we'd also like to be able to say that if a state isn't in this even superposition, then it's going to incur some high energy cost. So we need to bound the second highest eigenvalue of this matrix. Okay, fortunately, it's been looked at before. We're not the first people to have looked at this. So if I look at a slightly related, if I take I minus A, the identity minus A, I get this matrix B. And the eigenvalues of the two matrices are sort of related in this very simple way. Okay? If lambda is an eigenvalue of B, then 1 minus lambda is an eigenvalue of A. And this is actually a well-known, well-studied matrix. So let's take a look at it. What this is a random walk matrix on a line. Okay, so this describes the movement of a little particle taking a random walk on this line. I have at the endpoints, I stay with probably half, move inwards with probably a half. In the middle, I jump on either side with probably 1/2. Okay, so fortunately, this has been studied well, and so people are interested in. So remember, because we're taking I minus B, we're now looking at the largest and the second largest eigenvalue instead of the smallest and the second smallest. And the second largest eigenvalue of a random walk like this relates to the convergence time. Okay, so I'm not going to go through all the details, but it's known that the second largest eigenvalue of this matrix is 1 minus 1 over roughly t squared. Okay, and this tells me that the second largest eigenvalue of my original prop matrix is at least 1 over roughly t squared. Okay? So there's a question. Do you want to ask it and have me? Why is it? Oh, log t? Because I'm doing operations on these clock bits, okay? And I'm going from t to t plus 1. If I go from 0, 1, 1, 1, 1, 1 to 1, 0, 0, I'm changing log n bits. So the clock is log t bits long, and I could potentially change most of the bits in just going from t to t plus 1, okay?
But if this is the only problem, then it seems that you could solve it by some kind of array code, right?
We're actually going to go to a unary clock, which will solve it for us, yeah. Yeah, even simpler idea.
Array code, I think, doesn't solve it because you need to actually look at the entire, even though you're only changing one, in order to know which one to change, you need to look at the
Okay.
whole base.
But an even more simple-minded idea actually solves the problem, so, yeah.
Count with your finger.
Yes, exactly. Okay. Okay, so here's, now let's back to the computation part. So we don't want to just click our clock forward. We want to actually be executing gates as we go. Okay, so now this is our target ground state. And so basically what we want to have a constraint is that says if I find myself in state phi at time t minus 1, then at time t I had better be in phi with an extra gate ut applied. Okay, so that we want a constraint that says that. Here it is. Let's look at what it is. This little term here is diagonal in this matrix, or it's closed on this space of these two states. So these are the diagonal terms. This advances my clock. This goes from t minus 1 to t and applies a gate. This goes from t to t minus 1 and undoes the gate. Okay, so if I look at this term in the space spanned by these two states, I get this little 2 by 2 matrix. All right? We're good? And then we sum them all up. Okay? All right. So what we want to do is now think about what this thing looks like in the big space. Okay? Okay, so our space is really the Hilbert space of the input register plus the witness register. I'm kind of incorporating any ancillary qubits in here and then we have the clock. Okay, so we now have to think about what this term looks like in this big space. So let's define a basis for the space. So I'm going to first define a basis for the input register and the witness. So these are the inputs to the circuit. So if I pick a basis state from here and a basis state from here, that will give me a basis state for this combined Hilbert space. Okay? Now, one possible way to complete this basis is just to use all of the clock states. Okay? If I wrote my matrix in this basis, it wouldn't have nice structure to it, so I'm going to select a different basis. So instead, what I'm going to do is pick a particular starting state, okay, from my basis. And as the clock advances, I'm going to take the states of the circuit at each time step corresponding to using this vector as my starting state. Okay? And a little argument. So I'm defining the space that's sort of closed on this set of vectors. Okay? And the claim is that this will give me an actual basis. So I could give you the unitary, but instead let's just argue that these spaces are mutually orthogonal to each other. Okay? So if I take two different states that have different clock states, they're certainly orthogonal to each other because the clocks are orthogonal. Okay, so what happens if I take two states that have the same clock state? Okay, so if I start with two different basis states, they're certainly orthogonal to each other because they're different basis states, and this is an orthonormal basis. Okay, and now I just apply this unitary to each, and they're still going to be orthogonal to each other. Okay, so as long as they're coming from these different subspaces, even if they have the same clock state, they're going to be orthogonal. So it's going to be an orthonormal basis because it has the right dimension, and it's orthonormal. Okay, so now let's talk about what my propagation Hamiltonian looks like when I write it in this basis. Okay? Here's that span again.
Is fixed or K?
I have one for each JK combination. I have one of these guys. Okay? So the nice thing is that H prop, this propagation Hamiltonian, is closed on this subspace. Okay? And when I express this in this particular basis, I get this nice propagation matrix that we know how to analyze and understand. Okay? So the idea is, let's just walk through a couple. The H1 term is closed on these two states, okay, and gives me one of those little 2 by 2 1/2 matrices that goes in this corner, okay. The H2 term is closed on this space and gives me the next one, and the next one, and the next one on down. So if I look at my propagation Hamiltonian limited to this subspace and expressed in this basis, I get this nice structured matrix that I know how to analyze.
Just to make sure, you mean that it's block diagonal where each JK defines a block?
Yes, so that's this picture. So yeah, so the big matrix looks like this. So each JK has its own block. And then what we were arguing before is that if I look at what's inside a block is I get one of these nice propagation. Okay? Okay, so I don't know. Yeah.
Lanchas basis or something like that?
What's that?
Don't chemists call this a Lanchas basis?
Oh, I don't know what chemists would call it. If there's a chemist in the room, they might know. All right? Okay, so let's talk about the null space of this matrix. Each one of these little squares gives me one ground state. Okay? And so the null space, the zero eigenspace, is any superposition of states that look like this. Yes, I have a question. I'm just meaning the ground space, yes. Yeah. Okay, so I have for each one of these little squares, I get one of these states, okay, that's sitting in the ground space, okay? And so any superposition of states of this variety will also give me another zero eigenstate. So if I take a superposition of states that look like this, I can switch the summations, and what I get is the computation state now where the starting state is a superposition of different starting states from my basis. Does that make sense? Okay, so just the swapping of the, so that tells me that basically the null space consists of all valid computation states. Okay, and the second largest eigenvalue of this entire matrix is bounded below by 1 over t squared. Yeah. Oh, yeah, thank you. Second smallest. We'll debug these slides as we go. Okay. All right? Okay, so two more terms I need in my Hamiltonian. That's propagation. We kind of understand that pretty well now. We need to enforce that the input register starts with the input that we want it to. So it starts with x. So we add this additional clock term that says, if the clock is in state 0, and bit j of the input register is not what it's supposed to be, then I add some energy. Okay, and I sum this up over all the bits. So this adds a 1 energy for states with have a clock state 0 that have a bit that's wrong somewhere in the input. All right? And now I need to have a term that says that my computation is accepting. Okay? So that says I'm going to have an energy penalty if I'm at the final state of my clock, and the output bit of my computation is 0. Okay? And then my whole Hamiltonian is the sum of all of these. All right? Okay, so let's do completeness first because that's easiest. Okay? To show that if the computation really is accepting, like there is a witness that accepts with high probability, then I have a low energy state. you know what that ground state is going to be. It's just the computation state, starting with the correct input value, starting with the good witness that causes my circuit to accept. Okay? So term by term, H prop is 0 because this is a valid computation state. H init is 0 because whenever the clock is 0, X is exactly what it's supposed to be, so no bits are wrong. Okay? And finally, H out, let's look at what happens. Well, the only state here that's going to get any, have an energy penalty is if the clock is in state T. So the part of this sum where the clock is in state T is here, and this is the final output of the circuit. Okay, so this is the final state of the circuit, and I'm now just expressing it to separate out that output qubit, whether it's 0 or 1. I can express it as a superposition of the states where it's 1 and when it's 0. So we know that our circuit accepts with high probability. So therefore, we know that this magnitude squared has to be small. So this is the probability of rejection, which is going to be small if my circuit accepts with high probability. Okay, so that's the upper bound here. All right?
So you're first amplifying so that the reject probability.
Yeah, I'm assuming I've done all the amplification. So, yeah. We did that we did the hard work for that last time. So.
But this is, you pay for it and your T is going to be actually like
Yeah.
amplification T. So
Yeah.
It's,
What's the polynomial factor among friends? Yeah, okay. So I said this is what I set my lower threshold to be. Okay. Okay, soundness. I don't know how much of the actual, I'm going to give intuition and then I'll figure out how much I can actually walk through. So here's the intuition. So each one of these squares has only one ground state. Okay, there it is. It's the computation state starting with a particular basis pair. If this guy here is not the correct input, then it's going to get hit with H init. So there's going to be at least a 1 somewhere on this diagonal because when we apply H init to this state, it's going to have a charge of at least 1 here because this guy is not equal to X. Okay? So that means that the ground state of the H prop part of the Hamiltonian is going to have a high energy with respect to the H init part of the Hamiltonian. Okay? So this obviously has to be made more formally, okay? But this is sort of the rough intuition. Okay? So the only chance so I'm looking at the 0 eigenstate of the H prop part of the Hamiltonian and saying that if I'm in a box that's where the input isn't correct, it's going to have a high energy because of the H init part of the Hamiltonian. Okay?
Where is H init in the picture?
Oh, I didn't put it in there. So it's going to give me ones along some of these little diagonals here. Okay, so for example, I should have put it in the picture, but I didn't. So let's say we're in this particular square and AJ is not equal to X. At the 0 point, I'm going to have a 1 sitting on the diagonal there because of this term. All right? Yes?
Can you maybe just state the soundness claim? Just what are we trying to prove?
Oh, that's a good point. So this says, okay, so if my circuit doesn't accept, if the input is X, no matter what witness you give me, the circuit rejects with high probability. Okay? And what I want to translate that into is if X is not an accepting, it's not in the language, then this matrix, the lowest eigenvalue of this matrix, is bounded below by something 1 over poly. Because remember, we're solving local Hamiltonian, so we want the ground state of this Hamiltonian to tell us whether X is in the language or not. We did the X is in the language part, and if in that case, This Hamiltonian has a low eigenvalue. The smallest eigenvalue is less exponentially small. And now what we want to say, if x is not in the language, then the lowest eigenvalue is bounded from below. Okay? And we're using the fact, we're going to use, obviously very important, is that if x is not in the language, no matter what witness I start with here, it's going to reject with high probability. Okay? This part is just taking care of the squares where the input's just wrong. Okay? The next part is taking care of the squares where the input is correct, but now it's the H out part that's going to give us an energy penalty, because if I look at this ground state and I look at, you know, the time at time capital T, I get the final output of my circuit, and that has to be rejecting. If the input is X, no matter what witness I start with here, I'm going to reject with high probability, which means that this term is going to give me a high cost. I feel like we need like a moment of silence to just anyone want to formulate a question? Yes.
What exactly is the language that you are talking about?
Okay, we started with a generic language in QMA. What?
When you say language, in the same as language theory, for example, context-free language?
No. So a language is just a set of strings that are in the language or not in the language. And I want to determine, I'm given an X, and I'm saying, is my X in the language? The thing that makes this language special is that it sits in QMA, and it has this type of verification circuit that can, given the right quantum information, can verify that X is in the language. So that's sort of the core definition of QMA.
What's H out? In the picture.
And repeat the question.
Oh, in the picture. Okay, so yeah. So the question was, what is H out in my picture?
Yes.
That's not here, so I'm going to just tell you. So let's say this square actually has the right input. Okay? So this part, H in it, doesn't give me any penalty cost whatsoever. However, when I get to the final state of my computation, okay, when little t is equal to capital T and I'm at the final state, this state is the output of the circuit. And what H out does is it gives me a cost that's proportional to the probability of rejection.
So H in is the top, upmost top of the square,
If-
and H out is the bottom.
If I think of
bottom
0
right.
times 0 here and going forward here, the final state is sitting here, and this is going to have a 1 minus 1 over 2 to the n sitting there on the diagonal. That's the slide I should have made, so thank you for asking. Yeah. All right. Do you want to ask a question? Or
I thought
add something?
maybe it's useful to have an intuition where if everything is classical, everything is just classical, then everything is very simple, of course. And what's going on here is that you have 3 different types of constraints. One is that the input is correct. The other one, that's H in
H prop?
in it.
Yeah.
In
Oh,
it.
no, input is correct, yeah.
Then there's also the output is correct, meaning 1, it's accepted, and that the propagation is correct. And of course, if X is not in the language, you just cannot satisfy all these constraints. And since everything is classical, either the energy is zero or it's at least 1. Now, the thing with the quantum disturbing thing is that you have now being correct and not being correct means that the state lies in some subspace. And now, in the classical case, those subspaces are orthogonal, or the same. The subspace that corresponds to the out being correct or not is, I mean, everything is with right angles.
Yeah.
Whereas in the quantum case, the subspace that corresponds to all correct propagations, correct history states, may be not in a weird angle with the subspace of H in and H out. And And therefore you need to somehow say that the angle is at least something if x is not in the language. I don't know if that helps.
Did you have another question you want?
So,
Wait, do you want to hand him the mic?
so is I well understood if the string is in the language that will be expressed by a subspace. Is that the
No,
the
if the string is in the language, it corresponds to the lowest eigenvalue of this matrix. That's how I determine.
And what is the relationship between that and the subspaces? Because I am thinking in the von Neumann-Birkhoff quantum logic that is about reasoning with subspaces. And the complement is the negation.
So what we're considering now the case where x is not in the language, and we have to argue that this Hamiltonian that we've created has its lowest eigenvalue is bounded by below by something. And we're sort of arguing heuristically at this point, subspace by subspace. Okay? So I think I'm going to leave the intuition here. I have like 6 or 7 slides working it out, but I don't think we have time for that. I'd like to move on to the kind of unary clock. But the key lemma that Dorit was pointing to is that we have to argue something about the angle between the null spaces of these two Hamiltonians. So we have H in and H out, which sort of penalizes inputs that are incorrect or rejecting outputs. We have H prop, okay? We have to bound below the eigenvalue, the second lowest eigenvalue of each, and we have to argue that their null spaces have a good-sized angle between them, okay? And if that's the case, then we can lower bound the smallest eigenvalue of the sum by this relationship. It's the angle between the two null spaces and the lowest eigenvalue of each.
So if it didn't have a good angle between them, then what would that correspond to? Like,
It would mean that I could sit in the null. I could be in some state that's sort of close to the null space of each, and therefore have a fairly low cost. So only part of my state, a very small part of my state, is sitting in the perpendicular to either one. Yeah. Yeah. Yeah.
So is H in it not commuting with H prop?
H init is diagonal in this. I think it commutes. Yeah,
But
it
H
commutes.
out doesn't,
Oh no, H out doesn't. Yeah,
So
because
H out
H
is
out
the
is
trouble.
H out is it
H
doesn't.
out is the troublemaker kind of.
Yeah, and it has a fairly high weight on the diagonal because we've kind of pushed the probability in one direction or the other, but it's not completely diagonal. Yeah.
When you said the null space, should I think of the case where the null space is one-dimensional or it's huge?
It's huge, actually, because the null space of H prop is the set of all proper computation states for any starting point. So that's a big space, right? And then H init and H out are just testing whether the input is correct or not. So there's a lot of, so both are large subspaces.
And the issue is the angle between
Yes, yeah. Okay?
So it's like in Dirichlet problem, when you put differential equation, which kind of tells you about propagation, and you put boundary values, and then you have very small or zero space of solution.
Yeah. All right, so I'm going to skip over the next few slides, which basically works through this, okay? You can always, my slides will be posted, so you can work through the nitty-gritty details if you want, but I'd like to move on to the clock that sort of saves us the log n. You're following this in real time, I'm sure. Yeah. Okay, recap, this is what we did. We started with log n, now we want to prove to 5. And how's my time? Is anyone... Is anyone...
10 to 12 minutes.
Oh, I thought I lost some time there.
We started slightly.
Okay, all right. So here's my clock register. the thing that costs me is that this is expressed in binary. Incrementing a binary counter could involve changing a lot of qubits. Here's an example. So instead what I'm going to do is move to a unary clock. Okay? So now 0 is all zeros, 1s is all 1s, and each tick of the clock changes 1 qubit.
This is really practical.
Yeah. So this is an advance of the clock. This guy goes from 0 to 1. Okay, so now I can ignore the string of 1s and strings of 0s. In order to advance the clock, I need a 3-qubit operation. It's tempting to go to 2, and I will show in a second why that doesn't work. Okay, so but here I'm basically advancing this clock from t to t plus 1 by applying this 3-qubit operation to qubits t minus 1, t, and t plus 1. Okay? And that's 5 because 3 plus 2. So that's a 5-qubit operation. There it is, the 5-local Hamiltonian. So the h-init now, in order to test if I'm in time 0, I just look at that first qubit and ask, is it 0? Okay. In order to test if I'm at time t, I look at the last clock qubit and ask, is it 1? Okay. So there's a problem. Okay. Notice now that we've gone from a logarithmic number of qubits to a linear number of qubits. Okay. So the underlying Hilbert space has gone from polynomial size to exponential size. And I'm only using a tiny fraction of it for my clock. Okay, so what about the other clock states? And I have to basically add a term that invalidates them. Okay, and it's easy to invalidate them because the invalid clock states just have somewhere in them a 0 before a 1. So I can have this little term here that says, if anywhere you have a 0 before a 1, charge that state with an energy penalty. Okay. And in general, we'll use this mechanism later in talk 3 quite a bit. If I want to sort of create a penalty on a forbidden state and say I'd never want to see the state worry about it for my ground state, I add a term like this which sort of adds an energy. So we'll have a lot of these sort of little local terms that sort of create forbidden patterns sitting inside the ground state. Okay. So if we look at it's useful to think of the clock as a configuration graph. So I have a vertex for every standard basis state of the clock. So now I have a huge space. So it's 2 to the t plus 1 size. Okay. So I'm building a graph on 2 to the t plus 1 vertices. And I'm going to have an edge between 2 vertices if they relate to each other by one of the clock propagation terms. So for example, these 2 states have an edge between them because if I apply the propagation term to this one, I get this guy. Only one propagation term. So basically, if I look at my big 2 to the t by 2 to the t propagation matrix on the clock, for every one of these edges, I'm planting in one of those 2 by 2 1/2 matrices. Okay? Okay, so what does this graph look like? Well, it has this very nice structure to it. So here are my valid clock states. It's just a path. Okay? So this relates to this, relates to that. This is a big mess in terms of what the graph structure is. But the nice thing is that each one of these individual clock states has an energy penalty associated with it. So if I look at, this is just the clock matrix. I'm going to have one of these for every starting state in my basis, but just let's look at this for a second. Here's the space of valid clock states. Here's the space of invalid clock states. These guys have at least one on the diagonal somewhere because they have some forbidden pattern in them. And this guy is our favorite propagation matrix. So I can basically ignore this entire space because I know that the lowest eigenvalue is at least 1. All right. So why not a 2-qubit term? And the problem is that it can apply in places that you don't want it to apply. So if I look at this graph, yeah, it advances the clock by 1 here, but then you also get stuff like this happening. And you don't have this nice clean path structure anymore. Okay? There. Did I make it in time? Other questions for good?
Maybe give something about what you're going to do.
Yeah. If I remember, so I think you called it delta. I think you called delta I don't know, this interval that distinguishes between the acceptance and non-acceptance. And this delta shrank with n.
Yes.
Like, I don't know, logarithmically, like something.
I think I have it somewhere. So you can keep asking your question. I'll see if I can find it. Yeah. Here's my final E. This was tiny, exponentially small. And E plus delta is at least, I ended up with.
I'm not sure it's there was a gap between those answer you accepted and computations you did not accept. And this gap shrank with the size of the input.
Yes.
Right?
In fact, the size of the computation, which is the size of the, yeah.
So my question is, why is it the right condition? Somehow I would think that the longer the input, I should be more generous with delta rather than more stingy with delta. Does this question make sense to anybody except myself?
What does mean general?
Yeah, that is general.
No, that's the opposite. I make the test.
He says that the gap should shrink as the input size grows.
Yes.
Well, partly.
In the wrong direction. I should be more lenient with guys who try to do long computations and more stringent with guys who don't want to multiply 2 by 2.
Yeah, but my that second lightest eigenvalue shrinks with the size of my propagation matrix. Yeah, and that's sort of a deal breaker. Yeah.
It's technical.
Yeah, that's
Yeah.
technical. Ideological.
Oh, I don't have a deep reason for it.
No,
We'd like to keep it constant, but that's it.
Yeah, that's a big.
the deep reason is
No,
is
but
that
you require more than a constant. You allow it to shrink.
No, that's worse.
that's worse.
That's worse. Because you
Not more than a constant. We allow it to be 1 over over t squared.
You have to say something about promise problems, I think.
Perhaps I don't understand something about promise.
no, you are the circuit itself already guarantees you something. For any input, either you get high probability of acceptance or very low probability of acceptance. That's a big assumption. Most circuits won't do that. Being a good quantum algorithm means that you separate those that are accepted with very high probability and those, and some are not. So, for any,
But what about the gap between the cases where I can't say anything?
there isn't. We assume that for any x, any input, either it's accepted with high probability or any input and any auxiliary input will reject with high
But
probability.
in general, I'm expecting my spectrum to.
The statement is that you build a Hamiltonian which does not have eigenvalues between E and E plus delta. Simply does not have. This is about, of course, the bigger is delta, the more difficult it is to observe.
But
Because you want to have this space empty from eigenvalues.
yeah, and the denser, so the larger my space gets, the denser the spectrum, because the upper and lower bound are just growing with polynomial, but the number of eigenvalues I have in there is growing exponentially, so it becomes more and more dense. So that you're expecting that gap to get smaller.
Thank you.
Yeah.
Okay, good.
All right,
Okay,
good.
so let's thanks Sandy.